What's going on, physics gang? Time for a review of friction. Okay, so let's get the basics out of the way first, which is that friction is just the word we use when anything opposes something else, like two people getting into like a heated discussion, like there's some friction, right? So friction is any force that opposes the motion of an object. All right, so now there's actually a number of different ways of thinking about friction. We're going to stick with really just two basic ones, although I'm going to introduce just the idea of a third type of friction here. Okay, so static. So when something is static, we tend to misuse that word. Static means unchanging or not moving. So when we use the word static to mean maybe more of, I don't know, like a bad signal on your television or something, that's not the full word. It's it's static electricity because the word static means not moving. So when we say static electricity, we literally mean that there are electrical charges that are stuck somewhere because static means stuck. So remember, that's the real full word is not static, it's static electricity, meaning it's electrical charges that are not moving or unable to move. So similarly, when we're talking about an object that cannot move, that's static. So static friction is the amount of friction that prevents an object from even starting its motion. Okay? And this is, for our purposes, we can just say all the time greater than kinetic friction. I don't know if it's actually all the time. I think there may be some cases where kinetic friction is greater. But for our class, static friction, the friction that stops something from even unsticking from, let's say, the floor, that's always going to be greater than kinetic friction. So then what the heck is kinetic friction? Well, kinetic means moving, okay? So kinetic friction means the friction that exists between two surfaces that are moving past each other. Therefore, you could think about it as being called sliding friction. Our class is going to stick to kinetic, but you may hear it be called sliding friction in another circumstance. So this is the amount of friction that continues to oppose motion while an object is already sliding or moving. We're going to see that it's less than the static friction. Okay, so basically it's easier to keep something moving than to get it to start moving. Another type of friction we could think about is how a tire or a wheel works so well because you only have one point touching the floor at any one time, and that's called rolling friction. It's at the point of contact of a rolling object like a ball or a wheel, and it tends to be the lowest friction, which is why wheels are awesome. Okay, so let's get something simple out of the way. Even if we have not gotten up to the topic of work and energy yet, work is when you make something move by using force. That's literally the definition of work. So if you drag or push an object that's touching another surface, right, there's going to be friction. So when you do work against friction, meaning sliding an object on a surface, we know what happens, right? Rub your hands together. When you have friction, there's an increase in the heat buildup. And this is called the internal energy. You might recognize the symbol Q. It can be a capital or a lowercase q from chemistry. That stands for heat. So if somebody, cough, cough, if somebody asks you on a test or a quiz, what happens when work is done against friction is that there's a buildup of heat, also known as the internal energy of a system. We observe this in everyday life that when, like, let's say I rub my hands together, we notice that there's an increase in temperature, but that's because there's really an increase in heat energy first. Okay, there we go. All right, so now what about the forces acting on an object? So first we know the easy part, which is weight is mass times gravity, right? You get the weight of an object by calculating mass times gravity. Weight is actually a force. So the symbol for weight is Fg. The thing, though, is that we have to go back to Newton's third law, right? Which is that every force causes an equal and opposite force. So when an object pushes on the floor pushes back equally. Because this is at a right angle to the floor, meaning straight up, this is called the normal force from normala in Latin, which means at a right angle. So the normal force is how much the floor pushes back up. It's the same as the weight, but pointing upwards. Whatever direction something is getting pulled or pushed could be called the applied force. A way that I kind of remember this is whatever direction something is trying to be accelerated. Remember that. That may not be a good idea though, because if there's only friction, the object will accelerate towards the friction. Anyway, and friction is always opposite in direction to the applied force. So friction is trying to stop the stuff from moving. Okay, so a few examples of situations here. If there is no unbalanced force, like let's say static friction has not been overcome, that means that the object will remain at rest. It will not move. So if the applied force cannot overcome the static friction, the object continues to not move. If you notice, the static friction always tries to match the applied force, not always tries to match, it matches the applied force in magnitude, but it has opposite direction. Okay. In this little snippet, let's see if I show it here. Kinetic friction is less than static friction. So if I pause this, if you look at the number there, I think it says 188. I know it's not very clear. 188 is less than the oh wait, oh, you know what? Hold on. That didn't work as well as I thought. Pause. You know what? I'm just going to go to the simulator. Here, I'll show you. Ready? So I'm going to start applying force. Now keep your eye on the red arrow. Oh, I broke it already. All right, you know what? I want a little bit heavier of a thing. I'll put 2 blocks. All right, watch it again. So keep your eye on what's happening. So as I apply force, the friction force matches it exactly, and the stuff is not moving yet. See? 161, 164, increasing force, still won't move. Keep your eye on the red arrow, the friction. Keep your eye on the red arrow. Oh, did you see what just happened? I think it broke around 255 newtons. So you see how this is static friction. The object won't move, won't budge, won't budge. But if you notice the friction, it drops immediately when I beat the static friction. So I think it happened. Oh, it was around 250 something. You notice how it went from 250 something down to 188? This is the kinetic friction. The kinetic friction is lower than the static friction, meaning it's easier to keep something sliding than to get it to start sliding. Okay? So there we go. So once you get something moving, the kinetic friction is less than the static friction. I think I should remake that video. That didn't come out as well as I had hoped. Okay. Now, this one, though, I think worked out well, which is if the force that is being applied is exactly equal to the frictional force, then something could continue moving. It will just be at a constant velocity. It will not accelerate. It will not speed up or slow down. So that's something we have to remember, is that when forces are balanced out to zero, there are 2 options. All right, this goes back to Newton's first law of motion, right? If there's no unbalanced force, there's no acceleration. But no acceleration doesn't mean that something is staying still. Something could be moving with constant velocity. And then it brings us to Albert Einstein's theory of relativity, which is even weirder because that means, and this is real, right? Staying still at rest is the same thing as moving with constant velocity. There is no difference. Okay? So when applied force is equal to kinetic friction, an object will move with a constant velocity. The forces are balanced, meaning the net force is 0, so acceleration equals 0, right? Acceleration equals 0. However, that doesn't necessarily mean that velocity is 0. It could be 0 velocity, or something could be moving with constant velocity. Okay, so let's get to the nitty-gritty. So the coefficient of friction is, if we do some algebra with the frictional equation here, we could see that coefficient of friction is the amount of frictional force divided by the normal force, which is how hard the floor is pushing up on something. But how about we put this in easy terms? Coefficient of friction, with the lowercase Greek letter mu, which honestly, you could just use a lowercase u. It's essentially how sticky or slippery surfaces are with each other. So the greater the number, the more sticky the surfaces are with each other. The smaller the number, the less sticky surfaces are. And we can see these, a couple of values on the cover page of the physics reference table. See where it is? Okay. Now we know how to read this a little bit better. If objects are being pushed or pulled and cannot even move yet, then we will use static friction. Okay. If objects are being pushed or pulled and they're sliding, then we use kinetic friction. All right. So again, when things are able to be moved, then we can use static friction. If something cannot be moved, we use static. And if something's able to slide, we use kinetic. Okay. Now, the equation itself is not too hard. To find the frictional force acting on something, we just take the coefficient of friction and multiply that by the normal force. Okay. By the way, coefficient of friction, if you look, it's force divided by force, which would be newtons divided by newtons, meaning just like a percent, there are no units, they all cancel out. Okay. And let's remember that normal force is just weight, which is mass times gravity. Okay, why don't we try to do one problem that is related to that? So let's try to do one problem before we do something more tricky, and then I'll end the video. Okay, let's try to work out a friction problem. Let's make up a friction problem. Okay, so this will be a problem about friction on a horizontal level surface. So no hills, no inclines. Okay, so let's make something up here. Let's say that the mass is, I don't know, 88 kilograms. I don't know. And let's say that it has a initial velocity of 0 meters per second, meaning the object is not moving. Let's check that reference table. Let's see what surfaces they give us that are in contact. Why don't we go with rubber on wet asphalt? Oh, they only give us kinetic. So, all right. So I'll use rubber on asphalt dry. Okay. So there's a rubber object on dry asphalt, which is what the dark surface on a roadway is. So this is going to be a rubber object on dry asphalt. Okay, and there's another thing that we have to remember is always present with us, and it's not going to be given directly in a question for the most part. You're on the surface of Earth, therefore we always have the acceleration due to Earth's gravity, which is 9.81 meters per second squared. Again, it won't be probably given to you in a question, so that's a good reason to make sure that you write it down. Gravity is 9.81 meters per second squared. Okay, so now what we could do is solve for the amount of friction that would have to be overcome in order to get this object to start it sliding. So why don't we say that the first thing we'll answer is, what is the static friction that would have to be beaten in order to start this object sliding? So let's go get the equations we need. So let's check. We have the equation for friction, which is coefficient of friction times normal force. Let's start there. So friction equals coefficient of friction times normal force. Cool. What the heck is normal force? Okay, well, normal force is the same as gravity. So if we take the equation that has gravity equals weight over mass, why don't we go from there? So we're going to take this equation, and even though you know some of this already, I'll still recap on it. So normal force, oh crap, okay, normal force is equal to weight. So we can remember that normal force is the same thing as weight. The problem is, the frick is weight. Okay, so let's go back to that equation that's given to us. It's given to us as gravity is equal to weight divided by mass. But if we just do some algebra and cross multiply, right? Let's see. We could put this over 1, so it'll be Fg times 1, and then mass will multiply to the top, gravity. So that gives us a really easy equation that we know, which is that weight is equal to mass times gravity. And if we get that, that will give us the normal force. So basically, you want to start off any question by just getting the weight of the object. So let's do it. Let's plug in. The mass of the object is 88 kilograms, and Earth's gravity is 9.81 meters per second squared. Okay, so therefore the weight of the object will be 88 times gravity, 862.99. So like 863 newtons. Okay, don't forget a newton is the same thing as kilograms times meters per second squared. So you could either leave it as kilograms times meters per second squared or change it to newtons, because that's what a newton is. Okay, now we have the normal force. So let's go back to that equation. So what is it? We have the frictional force, in this case static friction, is going to be the coefficient of friction times the normal force. All right, so now we have to go back to that table. What is the coefficient of static friction, because this thing cannot move yet? What is the coefficient of static friction for rubber on dry asphalt? Back to the top, back to the tizzy top. All right, here we are. Rubber on dry asphalt, static, 0.85. There we go. So this will be 0.85 times, now we know that the weight of the object is 863 newtons, but that's also the normal force. So if I draw a crappy picture here, or a free body diagram, if we know that the weight is 863 newtons, that means that the normal force of the floor pushing back up is also 863 newtons. So we're going to multiply that by 863 newtons and see what we get. So it's the last answer I had, times 0.85. 733.54. I'll just round it to a nice cool 734 newtons. There we go. 734, oops, what did I just do? 734 newtons is the static friction, stopping this thing from even moving. Okay, now we could do one more thing. If you were to drag this rubber with constant velocity, what would be the kinetic friction? So what is the kinetic friction? And for that, the rubber would be sliding at constant velocity. So again, now the rubber, if it's sliding, that means it's moving. So we're going to use the kinetic friction, the coefficient of kinetic friction. So let's do it again. So this would be the force of friction is equal to the coefficient of friction times the normal force. Oops, I keep drawing the wrong letter. Normal force. But now, if the rubber is sliding, we will use rubber on dry asphalt kinetic friction, 0.67. So if the rubber is moving, we'll use 0.67 and then multiply that by the weight, which is the same as the normal force. So that's going to be times 863 newtons. And let's see what happens. So 0.67 times 863. The frictional force, the kinetic frictional force when the rubber block is sliding will be 578. So now we can confirm that the static friction is greater than the kinetic friction. And that's really it. Here, I'll wrap it up by just drawing a terrible free body diagram of what's happening. But we have the normal force, the weight, and we'll say that it's got an applied force and a frictional force. So frictional force, and then it's getting pulled to the right. So we know that the normal force and the weight are 863 newtons, 863 newtons. And if we calculated that the kinetic friction is 578 newtons, and it's moving with constant velocity, that means that all forces are balanced, which means that it must be getting pulled this way with 578 newtons. There you go. See why I stick to math? Can't draw. Okay, I hope that this helped somewhat. We'll do a more complicated question about something on an incline, like a hill, for the next problem in another video. Later.